Okay, let us continue. This is part 2, continuation of our design of 5-story building using response spectrum analysis. In previous video, the base here we obtained an equivalent lateral force procedure was, let's see here in the analysis output. Our base here along X is 1,699 kilonewton. And in G, along G direction is 1,859.42 kilonewton. Now for base here for RSA, along X is 1,701.29 kilonewton. And along G is 1,858.46 kilonewton. So both RSA and equivalent lateral force procedure are almost the same. So according to NASFE code, for all irregular structures, regardless of the ground motion representation, elastic response parameters may be reduced such that the corresponding design base shear is not less than 100% of the base shear determined in accordance with section 208.5.2. The corresponding reduced design seismic forces shall be used for design in accordance with section 203. So our ALF base here, BX, is equal to 1699.14 kilonewton. And then VG or V shear along G is equal to 1859.42. For the response spectrum, V shear along X is equal to 1702.06 kilonewton, while V shear along G is equal to 1,859.46 kilonewton. According to the NACP code that we read a while ago, Bx and Bg here must be equal to or greater than this value here. Since they are just equal, then we can use this B shear here in the design. Otherwise, we need to multiply each of this value here by a certain factor that would make these two ALF and response spectrum B shear equal. And this is according to the code. This is applicable to irregular structure. We can now proceed to design of members. So exit this and let us save first our file in the folder name RSA. So let's create the folder. Save. Then run analysis. Run analysis once again so that this file, including its analysis result, can be read by RCDC. Whenever we save a Staad file to another new folder, last step is to run the analysis. Done. Okay, let's close this file. Now let us open our RCDC software. Our design code here is in the drop-down menu. Select NACP. Browse. Desktop. RSA. Open. In the design element, let us take a look at beam first. Let's go to 4 meter level first. Then create project. So in this right side, this is the layout of our first floor. Our steel grid is 276 megapascal. Concrete grid is 21 megapascal. Click ductile design. Top and bottom detailing style. In the drop-down menu, select max dia. Maximum aggregate size is 20 mm. Our main steel bars ranges from 16 to 25. Then, click OK. Next, let us go to basic load cases. Settings, then basic load cases. Click design, auto design. Okay. All members in this level has no problem. We can check details of any members here. Let us go to design info tab. And in the right side is the layout of floor framing. We can check in this floor framing plan the continuity of members. Like for a certain grid line here, we immediately can determine if members have uniform or different sizes. If members have uniform size, we click one member and all are highlighted together as shown. If members have different sizes like here for example, if we have bigger beam here, next beams have smaller size. Then if we click this beam here, it is highlighted but others are not. And they are not designed as ductile beam. Meaning to say, they are grouped either differently by the software. In grid line 13, for example, we can check the beams here. Just highlight like that. Then in the left side, the highlighted beams is group G1. Let us check this G1 details. Go to reports in the above toolbar and in the drop-down menu, click elevation and section. Click G1. Then click OK. This is the elevation of beams grouped as G1. G1 has 3 beam spans. This is span 1, span 2, and span 3. And in the right side, it is also subdivided in 3 spans. Span 1, span 2, and span 3. In this lip span, this is the lip support. This is the mid span, and this is the right support. In the mid span, it is clear that the bottom of beam, based on this detail, is in tension, that it has more bottom bars than in the top bars. At the two supports, lip support and the right support, the top of beam is in tension. In this span, the spacing of stirrups is the same throughout the span. It has 44 two-leg 12 mm diameter stirrups spaced at 95 mm on center. So anyone can review details of reinforcement here, and even he can rearrange or even provide and make his own detailing, especially if it is impossible for him to provide straight bottom bars without a splice in this whole span, where the span length is L is equal to 15 meters. Now, let's take a look at the column. Click File New. browse, then here column, then create project. Let's go to settings, design settings, then click perform ductile design. Then special type of framing, enter 8.5 as response modification coefficient. Then uncheck optimize design. Then everything is in place, click OK. Let's proceed to reinforcement settings. Our column rebar ranges from 16 to 25 millimeter. Then click OK. In the column size tab, we can review column sizes here. Like for this column, here we can immediately check column sizes arrangement is correct. Bigger size should be at the bottom compared at the top, which this case is okay. If we have column layout like this, big column at the topmost, then in this dialog box, we would be able to catch this mistake and do corrections. In the level data, let us change the properties of steel reinforcement and concrete column here. Then let us navigate to basic load cases. While in this dialog box, if you are a skeptic on what load combinations the software may capture during the analysis and calculation, you can view in this dialog box the loads involved are DL, LL, rope live load, response spectrum along X, response spectrum along J, and wind loads. We can review the factors used in here. We can scroll up and down. Notice AX and AG are not here. So if everything is okay, then click OK to proceed. Since everything is in place, we can now proceed to design. Click design and then auto design. We can review column details here. Go to design input tab. Then in the right side, column numbering is visible and more visible if we zoom in. And just identify column we want to see details, like this column C1. For example, go to reports, then elevation, then click the plus sign to expand. Uncheck all columns and check C1. Then click OK. So this is the column detail of C1. We can adjust the settings depending on our goal. Like if we are not happy of this reinforcement and we want to see splices in the reverse, then we can manipulate the settings. Just exit from here. Then go to reports, elevation, check C1, and then click detailing. Detailing and drawing settings. Check here lapse settings and then click OK. So click OK. And so we can now see the lap at every mid-column height. If we want to review var cutting list on its column C1, go to BBS in toolbar. So exit this BBS, generate BBS, C1, then click detailing and drawing settings. You must be careful of your settings here. If you want staggered splicing and the location of splicing is every mid-column height, then check staggered and the locations. Then click OK. So everything here in the layout, in the elevation, everything here is accounted and listed here in the right side. And this is our bar cutting list. We can review everything in here from detailing down to calculations.